I'm Troy Schmidt, and this is my project proposal for lower limb exoskeleton stability using reinforcement learning to tune ankle strategy and central pattern generator. 12.1% of U.S. adults have difficulty walking or climbing upstairs, and another study shows that cane users compensate for their fear of falling by limiting their overall activity, leading to an accelerated decline in mobility. Lower limb exoskeletons are innovative wearable devices that can provide a mobility and rehabilitation solution for both sets of these impaired individuals. Unlike canes or walkers, lower limb exoskeletons offer active stability assistance to reduce falling, improved rehabilitation process, and stimulation to cardiopulmonary, metabolic, and muscular functions. Various control strategies have been used for exoskeletons. These control strategies can be used in conjunction with each other to control for stability and gait compliance. One strategy that has been used is divergent component of motion. This strategy is based on angular positions of the joints and pressure sensors at the bottom of the feet to estimate the center of mass and control for stability. In the case of walking, divergent component of motion, or known as DCM, offsets the center of mass slightly in front of the feet such that the user has a forward momentum while walking. Another control strategy used for stability is ankle strategy. The ankle joint may be the most important joint when it comes to stability. Your ankle joint is constantly active, keeping your center of mass above your foot. Ankle strategy relates to the DCM and the estimated location of the center of mass to adjust ankle torque due to disturbances. Focusing on gait compliance now, a strategy known as central pattern generator, or CPG, can be used. CPG is the control mechanism that defines the gait motion of lower limb exoskeletons using a series of differential equations. These differential equations are used to adjust gait frequency, oscillation amplitude, equilibrium position, and phase variation. Overall, CPG is used to adjust the torque of each joint to comply with a predetermined Fourier series gait pattern. Due to the complexity of having multiple torque inputs from the user as well as the exoskeleton, CPG requires real-time feedback to account for user inputs and adjusts motor torques accordingly. Finally, reinforcement learning is a strategy that can optimize system parameters to maximize stability and gait compliance. Reinforcement learning is a real-time technique that uses reward-based learning to update parameters. When the system makes desirable movements, the system is rewarded and is more likely to repeat that movement in the future. When the system makes undesirable movements, the system is penalized and is less likely to repeat those movements in the future. The reward function that contains the different rewards and penalties can be designed to tune real-time parameters such as power usage, gait speed, gait compliance, and vertical displacement of hip joints. The objective of this proposed project is to improve the stability of the EXO-H3 lower limb exoskeleton by adding ankle strategy and reinforcement learning to pre-existing central pattern generator and divergent component of motion strategies. Able-bodied individuals will be used for iterative testing for functions including standing up, sitting down, walking, and stabilizing with minor disturbances. A mobile computer will be used for the user interface to receive test results and observe the quantitative success of each result. There will be 4 major deliverables for this project. A plot of angular position versus time using reinforcement learning to tune ankle strategy and central pattern generator on Simulink. A plot of angular position versus time of a human-robot interaction, or HRI, EXO-H3 control test. A plot of angular position versus time of EXO-H3 controller implementation on an HRI test, and finally a video demonstration of the EXO-H3 HRI test. Evaluation metrics used to evaluate the success in this endeavor will be minimizing step time of real-time controller, minimizing the angular mean square error of motor positioning, minimizing the response time to disturbances in human-generated torque, and minimizing the power consumption of the exoskeleton. There will be 2 phases of this endeavor: simulation and human-robot interaction. Simulation will be used to test the quality and safety of the controller before applying the controller to the EXO-H3. Human-robot interaction will be used once the controller designed in the simulation is safe enough to be used on humans. Able-bodied individuals will be used to conduct iterative human-robot interaction testing. 3 main concerns may delay the success of the project: late delivery of the EXO-H3, hardware failure, and insufficient EXO-H3 processing speeds. Each of these concerns are related to delays in the progress due to the EXO-H3 physical model and can be accommodated by continuing progress on the Simulink model. Preliminary work has been completed for gait pattern generation. This work will be used to implement CPG and has provided insight on issues such as toe interference with the ground when walking. This work can also be used to set safety limits for the maximum and minimum angular positions of each joint. Preliminary work has also been completed for reinforcement learning. Using a MathWorks model, parameters from the gait pattern generation preliminary work were used to update this model. Other penalties were added, such as ground contact and damping coefficients of the ankle joints to reduce excessive oscillation when not in contact with the ground. The XOH3 is the ideal platform to implement new control strategies to aid in the mobility of impaired individuals. Unlike other lower limb exoskeletons, the XOH3 has actuated ankle joints and pressure sensors in the feet that provide the ability to implement improved stability techniques. Also, by implementing reinforcement learning, the XOH3 can deliver aid that would otherwise be inhibited by passive mobility aids, including canes and walkers. With active aid, the XOH3 can reduce the probability of falling due to disturbances and aid in clinical rehabilitation.